I'm a hydrogeologist. My motto in life is think out of the box. My name, Marcel. My experience, groundwater and soil contaminations. I'm the creator of Geo RGB, a channel of geographic information systems, GIS, geology, hydrogeology and contamination. The purpose, the objective, the goal, the intention, the target, the desire. Share my experience and knowledge to create points of discussion. The Geo RGB community. Promote the use of free and open source software. A free digital society. Provide technical advice to environmental companies. An opportunity for professional growth.
Hello guys and welcome back to my channel. In this occasion I'm presenting the Geostatistical Analysis course related to the creation of groundwater flow maps with Kriging Interpolation. We are going to be working with R and RStudio for the geostatistical analysis and graph design, and with Quantum GIS for the final map edition. We are going to compare the results we get with the geostatistical analysis extension of ArcGIS to see how we can get the same results. However, ArcGIS is a private software, but RStudio and Quantum GIS are open source and free software. I am going to create a series of video tutorials where you are going to learn how to create a Kriging interpolation successfully. Unfortunately, Kriging interpolation is a kind of black box where most of the people just press the button next without understanding what is the math behind the Kriging method. However, in R, there is no button for next. In these tutorials, I am going to explain with examples, step by step, the spatial analysis methodology, where I am going to be talking about exploratory data analysis, experimental semi-variogram, model semi-variogram, cross-validation, Kriging interpolation, and also, at the end, we are going to be working with the map edition with Quantum GIS and also reporting results. This is the 8th video of the Geostatistical Analysis course, and the topic for today is the cross-validation. We are going to be talking about how we can calculate the cross-validation and also the root mean square error using RStudio. We are going to create several graphs to make an interpretation of our data and to have better understanding of the mean of our results. Also, we are going to calculate the same parameters using ArcMap. Let's go to do it. At the previous video, we saw how we can calculate the directional and also the omnidirectional semi-variogram for the residual values using ArcMap. We were talking about the theoretical semi-variogram models. We was talking about the spherical model, the exponential model, and also the Gaussian model. And we make some explanations related with the components of the semi-variogram and also related with the shape of the graph for the different model semi-variograms. Then we created several models for the residual values with RStudio. At the end, we saw how to calculate the semi-variogram models using ArcMap. Remember that if you missed that video, you can hit the card located at the top right corner of your screen. Today we are going to see how to do the cross-validation and also how we can calculate the root mean square error. I remember in previous videos I said that we are going to work just with the experimental omnidirectional semi-variogram for the residual values for 3 models, for the exponential, for the Gaussian, and for the spherical. But at the end I decided to add one more model that is going to be a directional semi-variogram. That one is going to be, I'm going to show you, is going to be the directional experimental semi-variogram for the residual values for an angle of 135 degrees. Is this kind of green here is the one with the longest extension in our semi-variogram. Then in total we are going to do the Kriging Interpolation for 4 models. For all these 3, that is going to be omnidirectional one, and also we are going to do an spherical one for a direction of 135 degrees. All of them are going to be based on the residual values. Now what I'm going to do is create the model for the directional semi-variogram for 135 degrees. It's going to be this one, and that's the scripts I have. Then we're going to do for 135 degrees with a tolerance azimuth angle of 22.5 degrees for a lag distance of 15 meters, and it's going to be a total of 15 lags. Then 15 by 15 is going to be 225 meters, the total extension of our experimental directional semi-variogram. Then I'm going to run all this one, and then we can plot to see how it looks like. Is this one. Now what I'm going to do is fit the model. As I said, it's going to be just for the spherical one. Then I'm going to add here the parameters approximately. Okay, I'm going to run this one. We can see some information. We have a nugget that is close to 0, very, very close. The model is going to be the spherical one. The partial seal is 0.16, and the range is this one here. Now let's go to fit the line on the experimental semi-variogram. Is going to be this model. What we are going to do is create the Kriging interpolation for all these models and also for the directional model, and then we are going to create the maps, and we are going to do the same with ArcMap. Then we are going to compare the results we get with RStudio and also with ArcMap. Now let's go to see how works the cross validation. I have the script here. What I'm going to do first is to do the cross validation for the spherical omnidirectional model. And for this script, well, I'm going to run first and I'm going to explain later. This one is to see, that one is for the cross validation. That's the name I put to this object, and the script we are using is this one. That one means cross validation. And then we place our formula here. That is for a linear model. Remember, that one is related with the plane we remove from our data. Then here is where is our data and the model we are using. Then we are going to have a summary of our results. This kind of script provide information related with the predicted values. Is this one for the variance, for the observation values. This one is our data, the groundwater we measure at the field. This one is the residuals. In this case, the residuals is the difference between the predicted values and less the observed values. The difference between these two values is the residuals. And then also we have the set score, that is the residual divided by the standard deviation, and also we have the number of faults. Then in this summary for each of these parameters, we have the minimum value, we have the maximum value, we have the median, we have the mean, and we have the first quantile and the third quantile. Then, for example, if we want to make just a summary for the residual values, we can add this one. to our script to have just information only related with the residual values. As you can see, these values is the same as this one here. Sorry, for the residuals is the same as this one. Then if we plot to see what is the class of this object that we created, we can run this script, and what you are going to see is that this object is an spatial point data frame and is a SP. SP is a spatial data, as you have here. SP is spatial data. But if you try to see this object like a table, let's go to see this script here. What you are going to get is this ugly image that doesn't provide too much information, right? That's the reason, because spatial data, it's not good to see tables. We have to transform this object in a different one that we are going to do later. Then I'm going to do the same for the exponential one, omnidirectional. First we calculated the spherical one. Now I'm going to do the exponential one. I'm going to run all together. And then I'm going to do the same for the Gaussian model. And I'm going to do the same for the spherical model for 135 degrees. Now, as I said before, I'm going to transform just the exponential one, because for the rest is going to be the same. I'm going to change the name of object, and I'm going to create this one as a simple feature. With a simple feature, we can see the table with the data. That is because we added this one at the end of our script. Okay, you have to assume that this one and this one are the same, but what we make now is change the kind of object, right? This one, it was spatial data, and now what we are going to do is create a simple feature as a data frame. Okay, then I'm going to run this library, and I'm going to run this script here. Now we can see the class and compare with the other one. This one is a simple feature, data frame, and the other one we did previously. I'm going to run again this one, the class. As you can see, this one is a spatial point. Then now we can view the table with this script, and that's the table we have. As I said before, the first column, it's for the predicted values. The second column is the variance. The third column is the observed values. That's the data we get at the field when we measure the groundwater table, and we make the calculation to calculate the groundwater elevation. The residual values, in this case, sorry, I'm going to put this one in order. That's for the 57 piezometers, from 1 to 57. The residual values is the difference between the predictable value and the observed value. The zeta score, as I said before, is the residual divided by the standard deviation. The faults is the number of faults we have, and the geometry is related with the coordinates of each point, the UTM coordinates. Now we can do with QGplot a graph where we can make a representation of our cross-validation, and it's this graph. Now I'm going to talk about this graph with a different image, just to have an example. It's going to be this one. What we have here is the cross-validation, and here we have our data. That's the observation. That's this one here at the table. Cross-validation. The observed values is these values over here. And these values are in a vectorial layer. and this layer, the kind of geometry, is a point. Each point has an information. In this case is the groundwater elevation. Then when we are using our script, this script I'm going to show you here. When we are using this script, the create cross validation, we are creating a interpolated surface. The result is a raster layer, and this raster layer is built with pixels. Then each of these squares, it's a pixel, and each pixel has just one point of information. Okay, this one point of information. Then in this case, for example, we can say that we have a grid that is 10 by 10, and each pixel represents 0.5 by 0.5 meters. Then at the vector layer, we have just 4 points of information. But in the raster layer, we have 10 by 10 points of information. Here also at the vector layer, the information is presented in a discontinuous way because we have just 4 points of information. But at the raster layer, the information is presented very continuous because every pixel has a point of information. Then this one is the real model, the observed values, and this one is the predicted model with the predicted values. That's our model. Then as much data we have here, better is going to be our model. But more data means more money and more time. Then you have to look for an equilibrium of money, time, and the results you want to get with your model, right? Then at the end, if we overlap these two layers, we are going to have this layer here. And the cross validation, what it's doing is compare the observed values with the predicted values. Then, for example, for a piezometer 4, maybe we have a groundwater elevation that it's 93.333, and then we want to know, we know already what is the value of the observation, is this value here, but now we want to know what is the value for the pixel, and then compare these two values. For example, the value for the pixel is 93.222, right? And then the difference between these two values is the residual. That is that value over here. The residual value is this column here. That's the difference between these 2 points. And then the same for piezometer 3, piezometer 2, and piezometer 1, right? We want to compare the value with the observed value with the predicted value with the model. And when we have all these 8 values, 4 for the observed values and 4 for the predicted values, we can make an scatter plot. Let's go to start with this one, where we are going to put here the predicted values and here the observed values. Then if the values for the observed values and the predicted are the same, we are going to have all 4 points at the same line. If the observed value is the same as the predicted value here, and the same here, and the same here, and the same here, and we are going to have all these values in this line, and this line is going to make an angle of 45 degrees, and it means that the model for the location of these points, it's perfect, because the model the predicted values and the observed values are the same, then the model is perfect for these locations, right? And that's the kind of scenario we are looking for, right? Then we have the values for the reality, and we have the values for our model, and we want the values over here to be the same as here. That indicates that our model is going to be really good, right? But that it's not going to happen, right? The model is going to be very close to the reality, but never is going to be the reality. Then what happens in most of the cases, for example, in this case for piezometer 1, the predicted value has from here to here, and the observed value, let me change the color, the predicted is from here to here, and the observed value is from here to here, right? And the distance are different. Then, for example, for piezometer 2, we have this distance from here to here, and from here to here, and the same for piezometer 3 and piezometer 4, right? Then when we make the regression line for all these 4 piezometers, we are going to see that this line doesn't make an angle of 45 degrees. The red line is the ideal X scenario for a 45 degrees. That is this X scenario. That is the ideal one. But here in this case, the reality, the regression line, it's not an angle of 45 degrees. It's a little bit different. And that's indicated that the values for the predicted values and for the observed values are different between them. And that's what we can observe with the cross-validation to compare what is the ideal X scenario, that is the red line, the ideal one, with the X scenario we get with our model, the blue line. And that's what we can see here, right? We have the red line is the ideal S scenario, and the black one is the regression line for our model, related with the predicted and with the observed values. And in this case, as you can see, our model is really good because the regression line, that is the black one, fit really well with the 45 degrees red line. Then at the end, what we want for our model is that the difference between the predicted values and the observed values is 0. In that case, we are going to have all the points in a line that is going to create a regression line of 45 degrees with respect to the x-axis. That is the ideal X scenario. Also, with the data we have, we can play with the residuals and create, for example, an histogram. This is a histogram with the residuals. As you can see here, the distribution, it's really good. It's a kind of bell shape. As closer has your values to 0, that is better, because that it's indicating that the difference between the predicted and the residual values is small. And if you have high values at the extremes of the histogram, that it's a bad thing. But as you can see, in our case, most of the values are around 0. That it's a good X scenario also. Now let's go to calculate the root mean square error. And it's this equation here, where we have the root of the summation of the difference between the predicted and the observed values square divided by the number of samples. Going to make this one, going to show you here how it works. Then, for example, for the first model, I'm going to create this kind of object, and it's going to be for the spherical model, and the number we are going to get is the next one. And I would like to explain a little bit this script here. I'm going to make this one smaller. I'm going to put over here. I'm going to make this one smaller. and I'm going to put this one over here, right? What we have here is this one is for the root, this one. Then we have the summation, is this one here. Then we have here, this one is for the residuals, a square is this one, the residuals, then a square divided by the number of samples. Then in this case the number of samples is this one here, from here to here. Then we are going to do the same for the exponential model to see what is the error. Then for the Gaussian model, and the last one is going to be for the exponential model, but for the directional one. Let me see one thing here. Yeah, the directional one, 135. And then we can run this one. And as you can see here, the one who provides the minimum error is this one. This one is for the exponential one, for the omnidirectional. But as you can see, the spherical one for the omnidirectional, it's pretty similar. And also for the directional one, for the 135 degrees, for the spherical model, the difference is not really big with respect to this one. But for the Gaussian one, the error is almost the double. If you remember at the previous video when we was doing the automatically fit for the mathematical model, for the Gaussian one, the software after doing 200 iterations, it doesn't provide any result. Then we decided to force the fit doing the fit manually. But as you can see here, the Gaussian model is not really good. Then the last graph we are going to do for this video is going to be a bubble graph or a bubble map. It's pretty nice because here in this map we can see the difference between the predicted value with the observed value for the negative values and also for the positive values. Then we can see where we have the biggest difference, for example here around 0.5, also here and also here, but in general the difference it's not that bad. Then with the root mean square error, and also with the cross validation, we can say that our model it's really good. For the experimental omnidirectional semi-variogram for an exponential model. Now let's go to see how we can calculate the cross validation with RMap. Then go here, this option, then select your data, Kriging, co-Kriging. Next, we're going to use the ordinary one here, first order for removal. Next, that's the plane we are going to remove. Next, here we are going to put our parameters, 15 meters for the lag size and 15 lags. And we are going to do this example for a spherical model. And we are going to leave the rest of the parameters. Then next, we are going to talk about this section later in a different video. Next, and here we have the cross validation. We have this table with different parameters here as the one we calculated. Well, we have the measured values, that's the observed values, that's the predicted, that's the residual values, and the standard error, the standardized error, and also the normal value. And here we have different graphs and also different parameters. That's the number of samples, the mean for the residual values, the road mean square, the mean standardized, the road mean square standardized, and average standard error. Well, all these parameters can be also calculated with RStudio. Then we have different graphs. That's the one we did. I would like to make this one bigger. As you can see here, we have this blue line and also the other one. And this one is for the ideal scenario, and the other blue one, the one here, is for the regression line. Then we have here a graph where we have the measured values against the residual values. We can make this graph also, and also here different graphs. And we can make also the QQplot for the residual values. But here is not for the residuals, it's for the normal values against the standardized error. But we can make these graphs also with RStudio. Let's go to do it. Then finish here. Okay. And now what we are going to do here is to create the graphs. I'm going to paste over here. Paste, and these scripts. I'm going to separate this one, and I'm going to separate this one. Let's go to do this one first. And what we have here is the residuals versus the observed values. That's the values we have in our data. And then what we want in this graph is to have the regression line in 0. And in this case, it's not that bad. As you can see, it's very close to 0. And that's really good also to indicate the difference between the predicted values and the observed values are pretty similar. Then the next graph is going to be the QQplot, is this one, and this one is for the residual values to see if the residual values are normalized. We saw that one also with the histogram, but here in this graph, as you can see, most of the points are on the line, and that indicates also the residual values are pretty normal distributed. Okay guys, this is the end of this video. Thank you very much for watching, and see you on the next one, where we are going to be talking about the Kriging Interpolation.